Introduction to the S-model, or Ending Heuristics by Construction. The S-model is an extremely powerful and surprisingly elegant, though apparently novel tool to probe the distribution of prime numbers. In it, we'll find exact and straightforward constructions of heuristic formulas developed at the turn of the last century by Hardy and Littlewood and others. For example, the famous twin prime constant formula, this Euler product, has an exact interpretation in the S-model. Even the individual components in the product have precise meaning. In fact, there is no need to take limits. Examining the Euler product at some specific maximum prime tells us about structure beyond just a little RP squared. Perhaps most surprising of all is every such Euler product, for any difference greater than 1, has an exact interpretation in counting. Together, these Euler products interact with each other via a simple linear algebra. And this describes both the local structure of the prime numbers and the global structure of multiplication modulo p pound, the primorial of prime p. The key features of the S-model are the memory boundary must always be a primorial, and we start from the smallest primorial and grow to the largest, exercising a form of just-in-time memory allocation. The primorial is to primes, as the factorial is to the positive natural numbers including 0. Define p pound at m to be the product of all primes up to and including some mth prime. Note, the definition is recursive, just as in factorials. That is, the next primorial is the next prime times the current primorial. We choose primorial boundaries because there is a trivial natural construction which evolves one set to the next. But as we will discover, it will also reveal a beautiful natural counting machinery which counts member spacings, or gaps. Once we have sieved through some m, we can find the number of members in each set using Euler's quotient function. In our case, we have the count is equal to the product of each prime, where each prime has 1 subtracted from it. Note our notation, we introduce a negative superscript, and of course we will go on to generalize this. This introduces a general concept we call primorial minors. We denote as follows. The rth primorial minor is the product with each prime having the same integer value, r, subtracted from it. It can be any number, including 0. This means the primorial itself is a primorial minor. Following the normal rule for factorials, if the value before the operator evaluates to 0, the result becomes 1. That is, since 0 factorial is 1, our rth minor primorial is 1, when r prime equals r. and it is undefined for all prime numbers less than a. This also has a natural recursive form, though more complex. R next prime times our current primorial minor is R next minor primorial plus R times our current minor primorial. Notice how the minor index is introduced in the product. The proof follows trivially by adding nothing. We use the common trick of adding R and subtracting it. At each step, as we progress through successive primorials, we are actually looking at sets that describe multiplication modulo our current primorial. This has extremely important consequences, such as generating periodicity in the gaps on scales of multiple primorials. Notationize everything. Instead of writing the usual Z sub n, we'll denote it as capital S superscriptum, where n is the current primorial. We draw the set with multiple rows, the first row being our member O. We use a zero-based index, so the largest index is a current first minor primorial -1. Each following row is n differences between members. Given some index j, it is the nth plus j member, minus the jth member, where n is the zero-based row number. We name the second row the gap row. We name the following rows coalescence rows because, as we'll see, gap pairs sometimes coalesce into new gaps. We can write as many rows as we wish, which, given the periodic nature of the gaps, means we literally can do as many as we wish. Doing so gives us a probe to study tuples of length n. Once we have filled our set, we can actually abandon our co-prime member O, because trivially, our kth member is 1 plus the sum of the first k gaps. That is, from now on we can describe all the set structure through its gaps and gap tuples. This leads to the trivial construction of the construction given a construction. Or for brevity, the composite killing machine CKM. To build our next SM, we use the first minor primorial as guidance, namely, our next prime times our current first minor primorial. We want to expand our current set to the next boundary, is our next first minor primorial, plus our current minor primorial. Meaning, we have our current first minor primorial extra members, with a result from scaling by a new prime number. That is, we expand our next prime number copies of our current gap set to generate an intermediate set. This set now spans our next primorial, and is presieved through primes below our current prime number. This set has exactly our current first minor primorial, extra members, all composites of our next prime number. That is, every such member is either our next prime number, or its composite, and they can be found by multiplying our next prime number by each co-prime member of our current SM, because of our primorial minor algebra. Shorthand for this is, our next set is our next prime numbers worth of, expanding our current gap set, and removing the induced non-coprime members. The first stage we call expansion, and the second stage coalescence, or sometimes the CKM. Actually, for each member killed, it is the two gaps coalescing, hence the naming. Also, most of the new gap set looks the same as the progenitor set, as the mechanics is dominated by expansion, while the portion involved in coalescence is order 1, over our current first minor prime number. In the next video, we will show how the primorial minor algebra we introduced earlier drives the mechanics of gap distributions. For more information, please see the next lectures, or Google multiplication modulo n along the primorials, with its differences and variations, applied to the study of the distributions of prime number gaps.